Hi and welcome back. Today we're going to be starting to really delve into our HL content for organic chemistry. There'll be a few videos on this looking at different types of isomers, and then we'll move into some of the more complex reaction mechanisms that we need to know. So let's get started. Essentially, isomerism we've seen a few times already. We saw them when we first did organic chemistry, where we talked about alkanes, alkenes, and how we could have functional group where we can move the group along. So these would be positional isomers. So like one, so say we say butane 1-ol versus butane 2-ol. Okay, chain isomers are where we might have 2-methyl pentane. So we move a group or part of the chain along. Positional is where we can move the functional group along, so the double bond or the hydroxyl, something like that. Functional group isomers are where we can see that if we actually think about esters in this R, C double bond O, O, R, if we think about this, we can actually, this is a functional group isomer of a carboxylic acid. So if we break the R group up over here and put it over there, we actually get an isomer. These other ones, tautomerism and all these ones, we don't really need to know. It's only these three here that we tend to be familiar with already from the IB curriculum. The ones that we're going to start to look at now are actually what we call stereoisomers. So we have structural isomers and stereoisomers. And the two types of stereoisomers that we need to know for HL organic chemistry are geometric and optical. This video is going to look at geometric isomers, and this is where they differ in their spatial arrangement around a double bond. And then optical isomers are our 3D arrangements in space around a chiral carbon, which there is another video for. So when we talk about structural versus stereo, structural are always just moving a group. They have the same molecular formula but a different structural formula. So they have different connectivity, 1,2-dichloroethane or 1,1-dichloroethane. Stereoisomers, however, have the same molecular formula again, because remember, an isomer by definition has the same molecular formula, but they're connected in the same way, but their three-dimensional arrangement is different in space. So there's usually some restriction around the bond or something that makes them different in three-dimensional space. So these two are, of course, what we mentioned before, geometric and optical. So stereoisomers, by definition, same structural formula, different physical arrangement, and we divide these into geometric isomers and optical isomers. With the geometric, we will learn about cis and trans, as well as E and Z, and then for optical isomers, we have plus and minus or L and D. We don't need to be able to name optical isomers, just know that the different versions exist. However, for our geometric isomers, our cis, trans, E, Z, we will learn how we add that information into the name of our organic molecules. So let's look at geometric isomers more closely. Essentially, when we have restricted rotation around a bond, we can get a geometric isomer. This can occur when we have a carbon-carbon double bond or a ring structure within our molecule. It doesn't occur in carbon-carbon single bonds because these have free rotation around the bond. If the groups get too close together, they can just rotate and repel each other and they have that free movement. However, as soon as we put a double bond in there, we restrict that movement. So for a single bond, if the groups are positioned on different sides of the molecule, they're the same molecule because we can have that free rotation. There's no fixed point where they can't change their position. In a double bond, they're different molecules because they can no longer rotate around this bond. So whether or not the groups are positioned one on each side of the double bond or both on the same side of the double bond affects their reactivity and affects the polarity of the molecule, a whole bunch of different things. Overall, the position of the groups can change their reactivity. So the terms are cis for the same side and trans for across. So you can see here that the groups, if these are chlorines, then the chlorines are transecting across the double bond here, whereas in this configuration here, the two chlorines are on the same side, so we refer to this as the cis isomer. Okay, so this is trans 1,2-dichloroethane, and this is cis 1,2-dichloroethane. So anytime we have a double bond and groups across the double bond, then we're going to have this isomerism. Okay. We do need to have a look, though, that if the groups are the same here, okay, then we don't have isomers. We don't have geometric isomers. So if we have a look here, for a single CH3 group on this carbon, there's no cis-trans isomerism. Or if we have them where we have one on each side of the same carbon, no cis-trans isomerism. However, if we have two different groups on each carbon, as we do here and then here, we can have the groups that are different to hydrogen on the same side, or the groups that are the same, or the hydrogens on the same side. And then we can have a situation where we have, in this case, the two methyl groups would be considered trans to each other. Okay, so we see this with 1,2-dichloroethane, there is both a cis and a trans, and then we have the cis isomer of 2-butene and the trans isomer of 2-butene, where our methyl groups are either on the same side or they are on the opposite sides of the double bond. We see this same isomerism occurring with rings, because as soon as we join the chain together in a ring, we no longer have rotation. There is strain around that ring. So we can have cis and trans isomers of all our cyclic compounds. So this cis isomer here, which is 1,2-dibromocyclobutane, and then here the trans 1,2-dibromocyclobutane, but because we've got 4. It matters whether they are above or below the ring. We see this also with 6-membered rings, 3-membered rings, and usually we can use wedge and dash notation to help us identify these. Remembering that if we have wedges here, this is indicating that the groups are pointing out of the plane of the page. And then if they are dashed, it's indicating that they are going into behind the plane of the page, so they're going into the screen. So this gives us a way of representing 3 dimensions on our 2-dimensional surface. This is some examples. So we can see here that propane would not have a cis and trans isomer because it has free rotation around the bond. However, if we turn that into cyclopropane, now we have this situation where if we change the groups, because we have no rotation, we would start to see stereoisomers, those geometric isomers, appear. Okay, that's it for me in terms of identifying what our geometric isomers are in terms of cis and trans. Our next video, we will look at how we name these and the difference in identifying them between E and Z and cis and trans when we can use these two terminologies.